In this video, we're going to talk about all things cross-sections. Basically, how do I find the volume of a solid using what we call a known cross-section? Square, semicircle, these kinds of things, rectangle, right? So what we're going to do, our base scenario, is going to be this region R, which is going to represent the base of a solid, and it's going to be formed by the intersection of all those curves right there, right? So first thing we could do, as usual, right, is probably just draw it out. So y equals x over 4, that's just a line, right? So take your time, plot some things. I think the easiest thing to do is use that x equals 6 to our advantage. We're bounded by the x and y axis here, right? So if I start at 0, right, the question is where do I end by the time I get to 6? And so that's just 6 over 4. So that's really 3/2. So let's say right in the middle there. Okay, so basically I just have this line right here. I'm just going to note that this is that point right there, 6, 3/2, right? And I'm even just going to say, hey, we're going to cut it off right there, right? So the region they're talking about here, region R, is this region right here. So again, that serves as what they say the base of a solid. So imagine on your paper, you're looking at this, right? That is the base, and the solid is going to grow up from that. So what does that mean? Well, they need to specify what cross-section we're using. So in this first problem, kind of the most basic one, I'm going to use a square cross-section. What's that mean? That means that you have to think about just a geometric square, right? Just a two-dimensional shape. Here we go, square, right? But imagine, my analogy is always like, think of a cracker, like a Cheez-It or like a Wheat Thin or something like that, right? Imagine if you had a bunch of those in front of you and you took one of them and stood them on their end, stood them on their edge, right? And stuck it right here. Think about this little Cheez-It right here, right? But that Cheez-It is coming out at you. So like it's hard to see here, but if I had a desk, I would take that Cheez-It and I would glue it right here and it would be coming up from the desk. And imagine you take 100 of those, right? With one catch. Every Cheez-It is a different size because it's trying to mimic or match the curve, right? So really, when we think about it, when we talk about like the square, the size of a side of the square is completely dictated by the curve itself, right? Or in this case, the line. So when we talk about like, well, what do I do for my setup? The volume with cross sections is always based on some area function. That's really what we need. So it's really based on the shape that we're dealing with. So here we're dealing with a square. The area of a square is just length times width, or side squared, right? So what's most important for us is determining how do I represent that side of the square mathematically with what they've given me. And in this case, we can see if we just keep drawing little sides of Cheez-Its, right? That is really always going to be x over 4, no matter what, right? So I know that if one side of the square is x over 4, well, so is the other side. And if I know that, I know the area of the square, we'll call it a of x, right, is equal to length times width, or side squared, which is basically just x squared over 16. Or, if you don't even want to go that far, x over 4 quantity squared, right? So as with our other volume and area setups, right, what do we need? We need boundaries, we need a start, and we need a stop, right? And we can see that clearly in the picture. We're starting at 0, we're stopping at 6, right? So my volume here is no more than 0 to 6, and then the area function. So in this case, it's just the square area, right? That's it, because what that symbolizes is that symbolizes an infinite sum. That's really what the integral is, an infinite sum of all the areas that you could possibly have of all these squares if you stack them right next to each other and just glue all these Cheez-Its together, and then that's really what's creating your three-dimensional solid, right? Now what's important is, how does our approach change if they change the shape? So let's stay in the rectangular family, right, and go from square to rectangle, right? Now what's different? The different is rectangles don't necessarily have the same length and width, right? So what we're going to need to understand or know or be given is what are the dimensions of this rectangle? So look at this problem, right? We're still perpendicular to the x-axis, which means I'm still drawing, right, my sides of my square rectangle perpendicular to the x-axis, right? But now look what they say. The height of the rectangle is 3 times the length of its base, right? So now maybe change your visual. Change your visual. So here's x over 4, right? There's 6, right? But now, maybe you don't think of this as a Cheez-It. Think of it as more like a club cracker or like a graham cracker, right? Where one side is clearly shorter than the other, right? But they said here exactly how much bigger the height is. So if you think about it, if this, let's draw a rectangle, right? Okay, if this right here is still consistent with what we've been drawing here, that's still x over 4. That really hasn't changed, right? Depending on how you draw your rectangle. But this side of the rectangle has to be 3 times that. So all it really is that. That's it, right? Now you can see how our integrand is going to be affected. That's the only change we're going to make, right? So we're using an area function. The area of the rectangle is length times width. In this case, it would just be x over 4 times 3 times x over 4, right? And we don't have to get too fancy with how we write that either. So the volume in this case, still going from 0 to 6, right, is going to basically just be 3 times x over 4 squared. And that's it. That's the only difference. All right, how could they change this up? How could we see this in a different manner, right? Well, let's switch gears a little bit. Let's now deal with perpendicular cross sections to the y-axis. Same setup though, right? So here's the picture. Here we go. Boom. That's a 6, right? Remember this point was 6 comma 3 halves, right? So keep that in mind. But now what we're doing is when we kind of glue these things together, or we draw them, right? We're going this way, perpendicular to the y-axis. What does that mean for us in terms of setup? Just like we saw with volumes and discs and washers, right? Now everything has to be in terms of y. So my original function was y equals x over 4. That means I have to switch to x equals 4y. Right? That's a really, really big change here. In addition to that, right, my limits of integration will change. I'll have to go from low to high now. So I already know before I do much that this is now going to have to be from 0 to 3 halves. I can't go from 0 to 6 anymore, right? Okay, now let's take into account the shape. So let's handle a semicircle. So, again, we're trying to just do a little bit more condensed, right? So the idea here is that what we drew right there really represents the diameter of a semicircle. So in theory, let's come over here for a sec, right? What you see when I drew that little line right there, that is the diameter of a semicircle. Well, that diameter is the function 4y, right? That's exactly what it is. No matter where I draw it, I always get myself back to the curve, which we've now written as x equals 4y, right? Okay, so how does that play into what I'm doing here? Well, wait a minute. The area of a circle in general is pi r squared. This is a semicircle, so I got to cut it in half, right? Divided by 2. All right, well, remember, I need a radius, not a diameter. So if the diameter, let's call that d, is 4y, then the radius is really half of that, or 2y. So my setup is going to involve what? Pi r squared, okay, fine, right? All divided by 2. Right, see how everything's in terms of y, limits of integration are from low to high, right? So now I'm done, but if I want to clean up a little bit, I can go ahead and I can actually square that stuff and all that kind of good thing, right? So, I mean, if we look at what we're doing here, we can keep it. I mean, if you want to go further, you can make it, I guess you can make that 2y squared. You might remember us talking about this constant of pi over 8 when we do volume of cross sections with semicircles. There's a reason for that though. So if you think about what we just did from here to there, we split the diameter in half. So in theory, right, we are basically doing that, right? And then of course we're dividing it by 2. Well, if you square that, you'll notice that gives you 4, right? And then you're dividing by another 2. That's where the pi over 8 is really coming from. So in theory, that's I've always told you, hey, let's just do a pi over 8 over there. But that's where it's coming from, right? But this is sufficient. We don't really need to do anything more than that. One last one. What about if we were to do an equilateral triangle, right? Well, an equilateral triangle has also with it a very special constant, and that would be radical 3 over 4. So I know that I can kind of deal with radical 3 over 4. I can still go 0 to 3 over 2, right? But then the only other thing I need to do is handle it like as if it was a square. And I could have done the same thing here. Just handle it like it would have been a square. And so if it was a square, I would have just said, well, this is the side of a square. So I just got to square that, and I'm done. That's the only adjustment. I could have done that up here too. So if you just, maybe the last thing we'll do here is we'll just show you how really that is the same idea. If I change colors here, if I take that pi over 8 idea and tell you, hey, that's the shortcut we're going to do, right? What would the square be? The square would be this, right? Okay, why is this and that the same? Well, let's look carefully, right? If I square this, I get 16y squared divided by 8. That's 2y squared. Look here. If I square that, I get 4y squared divided by 2. That's 2y squared. So, and the pi is still there. So you can see that they are the same thing. They just had to take on a little bit of a different look. This is just more conceptual, how we got there. This is more shortcut oriented. So, hope this has been helpful. Good luck.